Hello. So let's talk about something actually very important to translate the demand of populations of consumer, a continuous of consumers with different valuations. So suppose you have a lot of consumers, we're going to use a continuous number of consumers, okay? I will normalize the size or the mass of the populations of consumers to 1. Okay, that's a continuous model. But now we are going to allow these consumers to have a range of different valuations. So valuations is the maximum they would be willing to pay for a particular good. Okay, so we have one perfectly divisible good, and here I have a graph that plots the density of the valuations. So in this axis here, I have valuations of the consumers, and in the vertical, I have the density that measures how many consumers have that particular valuation. And I have this curve here in black, okay? And the lowercase f is the density, okay? Evaluated values V, from V lower bar to V upper bar. So this V lower bar is the minimum valuation. Consumers that like the product the least, that's how much they would pay. And this V upper bar is the maximum valuation for the good. This value is the maximum valuation, this is the minimum valuation. And valuations belong to the closed interval between the minimum and the maximum valuation. Okay? So that's how much each consumer would pay. And consumers here have different valuations. The height measures approximately how many consumers have each possible valuation from this level to this level here. Okay, so here lots of consumers have valuations close to V upper bar. Not many consumers have valuations around here. Then more consumers have valuations like this, and I think the minimum is here. So very few consumers have valuations close to the minimum valuation. This is just an example, of course. You could have a flat function here. You could have a decreasing and increasing. This is just an example, a general example of valuation. So we're going to normalize the quantity or the mass or the measure of consumers to 1. So if I calculate the area from this point here to this point here, the area below this graph here is going to be 1. Okay? And the area is given by the cumulative distribution, this uppercase F. So F is lowercase is the density, F uppercase is the cumulative distribution of valuations. Okay? So it's going to F of any given value V here in the middle is just the area from this V lower bar to this point here. Okay? That is below the curve and above this axis. Okay? For those of you who know calculus, that's the formula of the area. For if you don't understand calculus, don't worry. Okay? So we normalize the mass of consumers to 1. So what's the mass of consumers with valuations from some V0 to some V1? So pick values V0 and V1 between the extreme values and say V0 is smaller or equal to V1, and I want to know how many consumers have valuations above or equal to V0 and below V1. And that's this blue area here. Okay? From V0 here in blue to V1 here, the area above the axis and below the curve. Okay? That's the number of consumers with valuations equal or above V0 and equal or below V1. Okay, this area here represents how many consumers we have this valuation. So the quantity of consumers with valuations from V0 to V1 is this area here. If you know calculus, you know that's the integral of the density function from V0 to V1, or the cumulative distribution up to V1 minus the cumulative distribution to V0. So this here is just, I'm saying this blue area here is equal to the area if I were to start here, go all the way to V0, V1, this area, minus this little strip here, the area from here to here. Subtract this little strip, which is this. Okay? So the area from V0 to V1 is the area from V lower bar to V1 minus the area from V lower bar to V0. That's what this formula is telling. Okay? And how do we transport all of this machinery to our usual price quantity diagrams? Okay? Well, that's in that case, we do this, the quantity, so I have the maximum valuation, V upper bar, the minimum valuation. Okay? So if prices are above this, if a price is here, my demand is 0. Nobody will pay this price. People, even the consumer that values the most value only V upper bar. If I have a price here, then everybody will. So the demand would be this point here, 1. All consumers would be willing to pay this price here. Okay? And for intermediate values from prices P0 above V lower bar and below V upper bar, the demand is this much here. The cumulative distribution up to V upper bar minus the cumulative distribution up to this level, P0. So P0, imagine a P0 here in the middle. What are the consumers that would be willing to pay P0 for this? Well, those with valuations equal or above P0. So consumers here. So the demand would be this area here. Area from P0 to V upper bar. So the cumulative distribution up calculated at V upper bar minus the cumulative distribution calculated at P0. Or the integral from P0 to V upper bar of the density. Okay? Now, the cumulative distribution on V upper bar is 100%. So that's what you have. So the quantity of consumers that would pay P0 is this much here. Okay? So that's how you transport this to our usual way of doing things. Okay? Our cumulative distribution function is a function from V lower bar to V, for the interval from V lower bar, V upper bar, to numbers between 0 and 1. Okay? It's always weakly increasing function. Okay? Always V of this is F calculated at the smallest valuation is 0, F calculated at the largest valuation is 1, and if the density is non-zero, the function is strictly increasing. The density is always strictly positive, so the cumulative distribution is strictly increasing, which means that the density here, so here the demand curve is always decreasing. Okay, and if you take this equation here, Q equals 1 minus F calculated at P0, and you take the derivative of this equation, you find this. Okay, so the slope of this demand is the negative of the density. Okay, so the derivative of this, the derivative of 1 is 0, minus the derivative of the cumulative distribution is the density. Okay, so yeah, the density is always positive or 0, you put a minus, this is always downward sloping. Okay, so that's how you calculate things here. We are usually doing examples because the course doesn't require calculus. We are usually doing examples where our demand is a straight line here, it doesn't have these curvy shapes here, it's a straight line. That's a particular example where my density is a constant function. If my density is constant, then the distribution is the so-called uniform distribution, right? It's a particular example, but it could have any shape. In principle, we could use, if you know calculus, if you know a little bit of statistics, you can do this, the formulas, you can calculate things for any shape, right? Any differentiable shape, if the functions are differentiable, you can use calculus to do that, okay? But we usually, when this demand is made of a straight line here, it means the density is a constant function. Probably here, right? Because you want the area to be 1. Well, that's it. That's how we translate the distributions of valuations of consumers for a good into the actual demand function for the good. And here you can start to see that we are using the language of probability. It's important, right? It's important that you make the mental connection between calculus, to know the integrals, and statistics and probability, to use densities and cumulative distributions, and apply that in microeconomics. If you can make this mental connection and understand these things, you are in good shape. You're starting to understand economics. Okay? So this is quite simple. Review the video if necessary and try to get some intuition. Try to create your own examples. So for instance, what would happen if this graph here is a straight line going down or a straight line going up? What would happen to this slope here? Does it kind of represent this curve here? Why the slope is like this and like that and like this and like that? So try to make your own examples to get acquaintance, to get experience with these very important connections, okay? So this will be particularly important in more advanced courses. See you guys next time. Bye bye.